This recording is the second part the series talking about muscle mechanics. Now, the last recording I left off with talking about motor unit recruitment and the order in which motor unit types are recruited, and then the order in which they fatigued. So what I want to do is just talk just very briefly about muscle fatigue. Now, muscle fatigue is often described as where you have a decrease in the capacity, the performance capacity of muscles. If you can't maintain a certain expected force or power with it, and a number of things can contribute to muscle fatigue, and we can characterize them by where it originated, the location of it. We can classify them as peripheral fatigue or as central fatigue. Now, peripheral fatigue is anything starting from the point of the neuromuscular junction all the way to the point to get to the actin and myosin. If anything goes wrong, anything wrong with the T tubules, the number of neurotransmitter, the amount of energy that I am producing, the source of energy, there's a whole list of stuff that you have in your notes. Anything along that line could lead to peripheral fatigue. Now, central fatigue, this is where, say, the motor neurons are not functioning, or you've pretty much given up, is inhibiting the voluntary effort, or it could be psychological issues. So if you have decreased neural input to that muscle, that's an example of central fatigue. I don't want you to focus too much on muscle fatigue because there's so many things that can lead to muscle fatigue, but I do want to show you something that can illustrate muscle fatigue for you. Now, I had previously shown you a lab recording from when I did motor unit recruitment. Well, second part of that lab is what we would have students do is we wanted to show them demonstrate muscle fatigue. They determined what was the maximum amount of force they can contract using the hand dynamometer. And we said, okay, for this part of the lab, I want you to do about maybe 90% of what the maximum amount that you got from the previous experiment. And I want you to contract that dynamometer, relax, contract, relax, contract, pretty much at that pace. We didn't want them to contract, relax, and just kind of like, oh yeah, let's recover, and then do it again. No, you had to kind of try to get to that expected force every time and kind of keep at a certain rate. And we would monitor the EMG as well as how much force that they're generating. And so what would happen, so if I put the force up here at the top, and then this represents the EMG, we'll say this here was the expected force we wanted them to get. So they would squeeze, and I would have a certain level of EMG. And then we would have them squeeze again, and I got the EMG here. And then we have do it again, and you notice my force is the same, but I want you to watch this. Obviously, this is a little exaggerated. You notice the amplitude of this EMG is higher. My force, of course, I'm trying to draw it better. Say my force here is the same as I did before. Now, notice we did not recruit all our motor units to start with. So we were trying to go about 90% of what our maximum was. But at this point right there, that person fatigued, because what you would expect, if I see greater amplitude of the EMG, I would expect a greater force. And if they're doing this right, you will fatigue usually pretty much in the first 5 squeezes. Now, what's going to be more obvious to a student is when they're going along and and then all of a sudden you start seeing the force getting a little bit less and a little bit less, and they keep going along, it's getting a little bit less. And what we'll notice is this EMG, I'm not going to do it, it'll be the same amplitude all the way across, But notice the force is continuing to decline. Now, if someone actually reached what we call marked fatigue, at that point, if they reached marked fatigue, the EMG would drop off too. But here, what you would expect is if I have this much EMG going on, I would expect to have a greater force. But because of fatigue, you see it drop off. It's really cool to kind of show to students. And what you'll notice again is the force is starting to drop off. The motor units are fatiguing. Those type 2B were the first to fatigue. So you'll start really seeing force dropping. Then the type 2A is gone. And someone that can keep going on maybe just a little tiny bit like this or whatever, they're just those type 1, the slow oxidative are going, but you can't generate a lot of tension there. So this was just a good example to kind of showing you using a picture of muscle fatigue. What I want to do though is I want to talk about types of muscle contractions. So we do have the two that we're really going to talk about are isotonic and isometric. I really don't want to talk about isokinetic because those are hard to mimic in real life. You have to have specialized equipment to do isokinetic contractions. So I'm going to just put a big cross through that. I really want to talk about is isotonic versus isometric contractions. Now, isotonic are referred to as dynamic contractions because there you will see movement. With an isometric contraction, they're referred to as static, as you will not see movement. Now, isotonic contractions are named isotonic because iso means same. Tonos is a word that means tension. And so with this type of muscle contraction, once the tension is enough to the point where you see something moving, is the tension remains the same. So that's like same tension. And I'll show you some pictures in a moment. Isometric means same length. This type of muscle contraction, there's no change in muscle length. And we'll describe that in a little bit. So there's no movement. Because there's no movement, no distance, there's zero work. Now with isotonic contractions, we're going to divide it in two different types, concentric and eccentric contractions. Okay, so we're going to break that down into two types. So I'm going to show you an example of an isotonic contraction where we here have a muscle and we're trying to lift 2 kilograms. And what you'll notice is tension's increasing. It's not until you have enough tension build up to exceed that load, in this case it's 2 kilograms, that tension remains the same, hence the term isotonic. But what you'll notice in this situation, the muscle length has decreased. And so this type of muscle contraction is referred to as a concentric muscle contraction. So this picture is showing an illustration of a concentric muscle contraction. So you have a dumbbell in your hand and you're doing a bicep crawl, called bicep crawl. Is the biceps brachii, the brachialis, those are muscles that are going to be contracting concentrically. And with this one, the muscle tension exceeds the load and the muscle will shorten. So they call that a concentric contraction. Now with an eccentric contraction, there's a change in muscle length, but the muscle length is not going to shorten. The muscle actually lengthens. So as you're lowering that dumbbell, the biceps brachii, the brachialis muscles, these are flexors in your arm, is they're going to be contracting, but in this case, it's an eccentric contraction. And with the eccentric contraction, the muscle tension is less than the load and the muscle lengthens. And in this case, there's in your notes, it says it's due to contraction of another muscle or the pull of gravity. Now, I want you to just think about this, is when you're lowering the weight, there's actually the triceps brachii, which is an extensor in your arm, is actually What's mainly involved in lowering that weight, but the biceps muscle, biceps brachii was, as well as the brachialis muscle, are contracting also, but because of the effect of gravity and that pull on the muscle, it's actually acting as a control. It's controlling that descent of the weight, because if that muscle didn't contract at all, that weight would just fall right down real quick and you would have no control at this joint, at the elbow joint. So eccentric contractions, the muscle length gets larger, it lengthens. With a concentric contraction, muscle length shortens. So isotonic contractions, their dynamic contractions, the muscle length changes. Now, once we start seeing movement, the muscle tension remains the same. Now, with an isometric contraction, I'm going to show you isometric contraction. Here, I'm trying to do 6 kilograms. Now, what you'll notice over here, that 6 kilograms didn't move. But look at that muscle carefully. So you have the muscle here. Notice it's a little fatter here. Now, the muscle's contracting. You do have sliding with actin and myosin. You got cross bridge formation. But the entire muscle length itself did not change. But you'll notice that the belly of this muscle is getting bigger. You see some pulling here. So I can see a little bit of this here. But this is considered part of the muscle length. So the muscle length didn't change. So what's happening is you're building up tension, but that tension was not enough to exceed the load, the resistance placed on that muscle. And so the tension just wasn't enough, and you notice the length remained unchanged. Okay? So there's no change in muscle length with an isometric contraction. Okay? Now, last topic I want to mention is just muscle tone, just very briefly. Now, I'm going to go back to that recording where I was in lab and we would record that EMG activity coming from that muscle. And actually, I'll bring in a couple things with it. I think I don't have as much room on there. I'm going to do it on this picture. I had electrodes placed on the biceps of the student, as well as in the back on the triceps. And they were asked to lift a dumbbell, do a bicep curl, and then lower it down. And say right here would record the activity come from the biceps, and down here would be the activity coming from the triceps brachii. And I asked them, okay, start with a biceps curl. And so you got some electrical activity before we start, and then you start seeing something like this. And the triceps, you'd see some activity going on too, okay? And then they'd hold it up, and they said, now lower the weight. And so, see something like this. And here. Okay, so what you're seeing is this right here is them lifting the weight. This is about where they're halfway there, and they're still lifting. This is the point where they're about halfway. And when you're doing that biceps curl, the biceps brachii, the brachialis, in this case we have it over the biceps brachii, that is the principal muscle responsible for flexion at the elbow. And this muscle is contracting concentrically. So you see and what you're seeing is actually a principle of motor unit recruitment. The hardest thing when you're lifting that weight is getting it to the halfway point. And so at the halfway point, you see the greatest amplitude. We don't need to do as much to keep getting it further up to the very top. Now, when you lower the weight, what you'll notice, you see more of that activity coming from the triceps brachii. That is the major extensor. And that one's going to be the major muscle involved in extension at the elbow. And you see a similar thing again. You see the motor unit recruitment coming up. This is about halfway, and then you keep going down. And again, this is concentric contraction of that triceps brachii. But what you'll notice is while you're doing the biceps curl, I still see electrical activity coming from the triceps. When I lower that weight, I also see activity coming from the biceps. So these two here represent the eccentric contraction of those muscles during those activities. So when you're lifting a dumbbell, the principal mover is the biceps brachii. It's actually really the brachialis muscle, but that is doing a concentric contraction, but the triceps brachii is doing an eccentric contraction. They usually refer to the term is when you have these two muscles contracting together is coactivation of agonists and antagonist muscle groups, because the triceps antagonizes the triceps. Now, when you lower the dumbbell, when you're doing an elbow extension at the elbow, the triceps is the principal mover. That's doing concentric contraction. It's shortening, while the biceps is doing an eccentric contraction. That's lengthening. So that's a good way of illustrating what we just talked about versus eccentric and concentric contraction. Now, let's go back to this idea of muscle tone. Now, muscle tone, I didn't draw it because I'm trying to do this by hand. I said, when we start, we're still going to see a little activity here. I would see a little bit of activity here and even here. When you're actually not lifting that weight and you're just holding the weight, you're still seeing electrical activity coming from those muscles, because we all have a certain amount of muscle tone. So muscle tone, I'm going to go back here, is you have some motor units that are active to that muscle, not enough to produce any movement, but it's going to be, there's a reason why you want it, is you have some motor units always active. It's kind of going to allow muscles to kind of, I would say, use the example where you're playing baseball and you're leading off first base. You're kind of getting halfway to second. You don't have to go as far when someone hits the ball. So we're not stealing the base, but here it's kind of gets those muscles kind of almost there, get ready to go. When we do want to have muscle contraction, muscle tone also is important in maintaining optimal length tension relationships. It's also it's a good thing to have a certain amount of muscle tone, because that constant little bit of contraction that we have in there burns more calories at rest. You look better when you have a little bit more muscle tone. You don't want too much muscle tone, but there's always you want a certain level of muscle tone. So it's because those motor units, you have the nervous system firing on them, and so they have a certain level of tone, tension being developed, but not enough to produce any type of movement. Now, one last thing we'll remember is I want to go back to this picture again here, is now I want to bring in an isometric contraction. So in this lab, I made them do that, and then I said, let's try something else. Don't put the dumbbell in your hand. Grab a hold of the bench, bench top, which is not going to come off the floor. Say, try to lift that bench off the floor. And I say, okay, start lifting, try to lift up. It's not going anywhere. I said, start recording the machine. And if you're taking your hand, put, palm up, like trying to lift, try to get, so here's my left hand. Here's my palm. And I'm taking this part is right underneath the bench top, and I'm trying to lift. Is if you just kind of envision it, try to lift like your table up off the floor. Is if that table does move, it's your bicep. You can feel it in your biceps, okay? So what I said, okay, do it this way, and from the bicep, this is what I'm going to expect. Like that. I still have the electrodes on the tricep. So try to do it. I'm going to see electrical activity coming from both muscles. more from the biceps, because if I'm able to move that table, the biceps is going to be the primary mover. It's going to be the agonist. But what you'll notice is you compare this, I kind of try to keep it like that instead of doing this, that motor unit recruitment, because you've already recruited all the muscle units, or I should say all the motor units. Everything's already recruited. You don't recruit anymore. Now, if we had them turn their back to the table and put their hands, their palms down, and just think about if someone tried to do a tricep dip off it. But here I said, well, I want you to try to push down the table that way. And if you do it that way and the table does move, then the tricep is going to be the primary mover. And in this case, when they do it that way, you see more of the activity coming from the triceps, and you still see biceps, but it's not as much. So that was way of them kind of showing isometric contraction using the electromyogram. So it was kind of just a cool activity that we'd have the students do. So this will be the last bit of this recording on muscle mechanics.